I can be intrinsic geometry, exterior algebra in 3D. And this example here, for instance, is in two-dimensional. And you will see later a four-dimension. Now, B part 2, lecture 8D, numerical example, let's put in the singular here. And the push forward, okay, here is a push forward, attention now, from Cartesian to polar, okay? That's why this symbol K over here. And the pullback will be here from the polar to the Cartesian, see? Now, a function g at a point of this polar coordinate is a scalar quantity. It's easy for you to see. For instance, if you have a function, let's say z is equal f, x and y, okay, this is a function. Now, if you set a point, for instance, point x equal 1, y is equal 2, this implies that z here is a scalar, you see? So a function, when you apply a function to a point, this is a scalar. You see, it maps, for instance, the polar coordinates to the real number. That's quite clear, okay, as you see in this example over here. Now, you see, adjoint operator identity, you see? Now, this is identity. This here belongs to the polar, okay? I'm sorry, this over here belongs to the Cartesian, you see? And this one to the polar coordinates, you see? So this identity. Now, where xp, you see, is a push forward. Attention now. The symbol over here is the symbol here. Okay? The same symbol. Okay? As you can see over here. You see? Now, this is the identity. This simple example where we involve Cartesian coordinates and polar coordinates is just for you to grasp the application of this adjoint operator identity. How it is important when you study push forward and pull back. That's so. Now, given this vector over here, okay, this vector belongs to the Cartesian coordinates over here. So these are the components of this vector, and xp belongs to the polar coordinates. Okay, xr, x theta are the components of this vector xp. Now it's better to put over here a parenthesis. So see, this is parenthesis over here. Now, partial, this is it's a notation. Partial r here means derivative, partial derivative, okay, with respect to xr in this case. You see, there's a partial derivative with respect to x theta. There's a simplification of this notation over here. Now I want using the push forward the components xr, x theta in terms of xx and x and y. You see? Let's apply the adjoint operator identity. Okay? This is the left-hand side over here. These are the Cartesian coordinate, these are polar coordinates. xp, don't forget that. xp is just dfq or f star iyq. See, I just set over here just xp. Now, g, attention now, g is a function, okay? In this case, that belongs to the polar coordinates. And attention the term, the pullback of this function, okay? In this case, this belongs to the Cartesian coordinates. It's a pullback and push forward. So this, attention now, this side here, you see this side on the adjoint, is the same as this one. You see YQ, you see, acts on this F star G. Okay? Attention now, belong to the Cartesian coordinate, the adjoint operator. The right-hand side belongs to the polar coordinate. Okay? This is equation 1. So you compute, again, since the components are independent, I can set, firstly, G is equal G is equal R over here. So the pullback of R is just R here. You see? The pullback. Now, attention now. This pullback, this here, belongs to the Cartesian coordinate. You see? This is the Cartesian coordinate. G belongs to the polar coordinate. So this is square root of x squared per y squared, which is R. Now compute. You see, AX over here is just AX. BX is just, in this case, XY. Okay, exactly as I wrote before. See, from here, you see? Now I can write, okay? This is a very, very, very important property, okay? I will erase here just for you to remember this, okay? Which we derived in previous lecture. This is very, very important. When you have a vector x, when you act on a coordinate, for instance xi, this leads to the component, okay? Let's call ci. You see, suppose x is equal ci, then put here partial derivative respect to I plus partial respect to j. You see, x applied to xi, okay, give me exactly this component over here, okay? Instead of xi, let's put ci. Likewise, x applied, for instance, to cj, this leads to cj. I already derived this, okay, in detail, carefully, that's to show this important property. So that's I'm using, okay, this property over here. So let's continue here, okay? Now, y over q, attention now, yq of r, attention now, you see? This will give me the component, okay, of this vector, okay, using the variable r, you see? Now, for g is equal r, see, that's a function, okay? Now, f, the pullback, f asterisk r is just a repeat. This belongs to the Cartesian coordinates. Now, yr is equal xi, you see, this is a partial derivative. Attention now, you see, this is r, this r over here. This is r, this r over there. You see, as I said. Now, again, partial r respect to x, attention now, r is square root of x squared per y squared. You just take this derivative. This is a calculus, okay? The calculus in the first grade. You see? So this is a partial derivative. This is equal to x divided by r. R is square root of x squared per y squared. And the partial respect to y is y over r. So in this case also, then I have my vector, okay? This is equal, attention now. You see here, and here, I already derived over here. You see, you just plug this partial derivative and write down x divided by r and y divided by r, which is equation 2. On the other side, now I'll move to the other side, you see, of the adjoint operator identity. Now xp, I can expand. This is the same as x r. This is the same of x theta. You see, these are components. So, attention again, look the property here. The property. I just wrote over here. You see? No, attention now. X over here, xp applied to r is just the component of this vector. Okay? It's just what I said here. A vector, a component, leads to a component. See? That's clear from that demonstration.